Hello, friends. Welcome to the Georgia Tech AI podcast. My guest today is Batuhan Altundas, a PhD student at the Core Robotics Lab at Georgia Tech. He's worked extensively on human-robot collaboration, focusing on how robots can become effective teammates and not just be seen as tools. His seminal work has been on HybridNet, a deep learning framework that enables robots to understand and adapt to human patterns. I would now like to end with a few words by the famous roboticist Cynthia Brazil. Robotics is not about making machines to serve us. It's about creating machines that can be our true partners. Thank you very much. Humans and robots, they have unique strengths. Humans can be adaptable. Robots are very precise with whatever tasks they take on. What are some additional factors that you need to take into consideration when grappling the two?
Yeah, so robots can do jobs that we consider dull, dirty, or dangerous. So these are the three Ds that have come in robotics. And robots are really good at doing repetitive tasks over and over again that can be precise and that a human might not necessarily need to do. On the other hand, humans are, like you said, very adaptable and capable of learning new tasks very fast. You don't need someone to either program a human or give them long times of computational power to just like process the information and come up with something, some policy that will allow it to execute that task. So, like you said, humans are adaptable. On the other hand, robots can handle things that humans cannot, dangerous tasks, as we have seen in the Fukushima nuclear disaster in 2011, where robots were deployed to handle tasks that were unsafe for humans to complete and mitigate disasters.
People would think as robots get more advanced, it's full robotic teams that will do the job and be very effective. Why is it that we're not there yet? Why is it that human robot teams still outperform fully robotic teams?
That's a great question. I don't think humans will be entirely phased out. If we're looking for manufacturing jobs where we can generate an entire autonomous line, there will always be a need for humans to supervise it and make sure that something that's not foreseeable, that the robot has not encountered before, can be handled by a human. On the other hand, robots will start to get more close to humans and they will start working with humans for humans. And this can be in a house where you have now a robotic maid, let's say, that will take care of work that you may not like doing or you may not be able to do. So we have in our core robotics lab previous research done on especially elderly population and how they would react to having robots take care of tasks that they're starting to become unable to do.
Your research directly considers a human learning curve. There's a period, when you're collaborating with a robot, you're not very good at the task. And over time, you do get better. How do you factor that in when, you're scheduling between a human and a robot?
Yeah, so the basis of that research was done by Russian Leo and Manisha Natarajan, and they have conducted user studies on humans themselves to see how they would learn over time. They have actually used Lego assembly instructions to see how, if a human repeated the same instructions over and over again, assemble the same assembly line essentially, how their performance improved, how fast they became. And they managed to learn that, yes, humans learn, and you can actually model that learning curve and fit it in a curve. And then you can use that to predict how they will behave in the future, how their performance improves in the future. So that is one side of it. Now you have an agent that will learn over time, and that you might need to predict how it learns. And leveraging that is a real world problem. We have stuff like seasonal workers who have a very short duration to become experts in the job, and repetition brings that expertise. So you have that trade-off of immediate reward by having a robot do it versus having a human do it so they can get better over time.
How would a scheduling algorithm go about assigning tasks to the humans, that's us, and the robots to make sure the work gets done, but we also grow in the process?
So we assume that robots are static, as in they have a deterministic time on completing what task they're given, and that is something that's constant over iterations that robots do not necessarily learn in this context. Compared to humans who have a model, and that model itself over iterations actually shortens the time it would take to complete a task. How we achieve it is we utilize predictions, and we actually use the previous work to fit the human behavior, the first observations of the human, into the curve to predict how they would behave in the future. So then you have a cost-benefit analysis of which human learns faster and which one can be assigned.
You also have to consider, am I not overburdening them? In the beginning, they might not be very good at the task, so you don't want to give them too much work. You want them to get some space, get accustomed to what's going on. But once they're good at the task, you also don't want to bore them. Is that a consideration you're making?
It's certainly a consideration that can be analyzed, especially how much work has been produced by humans over robots. And that is something interesting that actually I had to conduct, because there was one bug in my code that I ran into where I have accidentally made the human model instantaneously complete any task given. So the result of the schedule that was learned, the policy that learned, was assign everything to humans because they can complete it very fast. So yes, that is something that we would have to consider.
What makes the problem so challenging is humans are so different. We have such different skill sets. Who knows? Sometimes, you and me, it might take me more time to do a particular task, say programming, than you would because you have more experience. So there are all these factors that you have to consider. I want to move into HybridNet, the scheduling algorithm that you had come up with. How do you account for heterogeneity, the fact that humans are so different and we have different tasks and we have different skill sets?
So the first assumption that we are making is that every agent can complete every task. So that is specifically for the paper that we have published. Future work will involve actually having limitations where only humans can complete some tasks over robots, and similarly only a certain subset of humans might be able to complete a single specific task. So how we model that is we use what's called graph neural networks, and they are especially useful in this context because it allows us to scale the problem up to both the number of agents and number of tasks. And then we have human agents that are represented as part of that graph as nodes, and robot agents that are also their own nodes. And then we have also tasks themselves as nodes. And then we have the relationships between these agents, be they robot or human, and the tasks that they can complete and how they perform. And this has been initially conducted by my co-author and mentor, Jaeyoung Wang, who graduated from his PhD in 2022. And his work was specifically on modeling task allocation of heterogeneous teams using graph neural networks. What we did with HybridNet is we took that work and we expanded upon it. Instead of using heterogeneous robots, now we have human and robot teams, and we also wanted to speed it up because graph neural networks, while they're good at scaling and they're relatively fast, there's also things to consider like training time as well as computational complexity. So how can we take a sequential decision-making model that scales with number of tasks and make it instantaneous?
One of your papers, Grand Challenges with Human Robot Teaming, one of the factors is scalability. Teams are going to get larger and real-world deployments are complicated. Do you think that this solution can scale to a lot more humans and agents
Yeah, so before we go into HybridNet, I want to specifically give a context on what other methods exist. So we have exact solvers, which are optimizers that use something like mixed interlinear programs to do constraint satisfaction problems, where we have these constraints and we are optimizing to reduce the time it takes for every agent to complete the entire set of tasks. But these do not scale because task allocation and scheduling is an optimization problem that's NP hard, which means it will scale non-polynomially with number of agents and number of tasks. It will make it infeasible at certain points, at certain scales, to use these exact solvers, even though they will generate the most efficient policy. On the other hand, we can use heuristics, which are way faster, but these heuristics are often algorithms like greedy algorithms where you're selecting a task that you can complete the fastest, but they don't necessarily scale up very well. They might perform really good at small scales where you have few agents and few tasks, but they don't scale that well. And then we have meta heuristics like genetic algorithms that take in these original heuristics and do a search using mutations and adding randomness. But like I said, it is adding randomness, so you do not have an actual guarantee on getting a schedule that's good. So what we do is we can train our model at small scale and deploy it at large scale. And we have shown in our experimental results that our models are able to scale up to approximately 50 agents. But like you said, there's also future work that needs to be conducted on what happens if you have not 50, but let's say 100, 200, or 1,000 agents or tasks.
How are we accounting for improvements over time with this heterogeneous network?
So the model that we have, that it takes in the current state, which is a combination of what was previously observed about humans to predict how they might behave at that instance if you assign a task to them at that point. And robots, which like we said, are deterministic. And then we have also stuff like stochasticity of humans. There is randomness involved in there. So these are all part of the feature space of the nodes that we train. And then we can use those features, process it through the neural network, and generate a policy where we are assigning in order a task to an agent. And once we have the entire schedule of task agent pairs, we process it, we evaluate it, we observe how the human actually behaves, and then we update our human model based on our new observations for the next step. And we do that for multiple iterations in the multi-round environment.
What's an LSTM propagator? How does that fit into your scheduling algorithm?
So an LSTM propagator, it is a recurrent neural network that takes in the initial representation of the environment generated by the graph neural network and produces over iterations task and agent assignments. And it uses an LSTM to essentially propagate that information of seeing what happens if I make one decision followed by the next. So if we have to compare it to how we think, we are taking in information from our eyes, our ears, compiling it all into a representation of the world. And then once we determine what we want to do or what we need to do, we come up with multiple steps without actually needing to observe the environment again.
I want to take a step back and ask you, in a human-robot teaming environment, say that I really trust my scheduling algorithm to give me the right answer. Is there a danger of over-reliance and the fact that you might be less situationally aware about what's going around you?
There's always room for human supervision. So if you have an optimizer, there's also stuff like trust in the system itself, the trust in the scheduler that you need to account for. So a human might choose not to follow that schedule. This is entirely up to them. Most of the time in manufacturing settings, especially, a human supervisor can change certain patterns. So in problems like nurse scheduling, where you are assigning nurses to patients, there are systems in place, there are optimizers that actually generate those schedules, but then you have some human observing and modifying those schedules based on their expertise.
What if the humans disagree?
Well, that's a good question. What if for other models, I cannot say, but for HybridNet itself, if a human decides to change a decision, the recurrence scheduler that is in charge of making the follow-up decisions will account for that specific human decision. So there's also that option. And I think that's a good future work that might be interesting.
We take into account preference ranking. We could pool all their votes together and decide, okay, this is what we should do because the majority agrees on this course of action.
Yes, so HybridNet actually learns a distribution. Specifically, it generates a probability mass function of tasks and agents. So it's first selecting an agent from a distribution, and then given that agent, it's selecting a task over another distribution. So there's always that ability to choose from multiple options. And it might actually be more beneficial to generate multiple schedules by sampling over those distributions and creating an ensemble of schedules where you pick the best one.
Let's take a sports game, for example. We instinctively know what the other player is doing based on all the knowledge that we have accrued from our past interactions, body language, just us knowing each other as humans. How do we take that a step further into human robot teams? You talked about the limitations associated with turn taking and the need for adaptive scheduling. Could you expand on that and how we can be more synergistic in terms of how we team with robots?
So for human robot teams, or essentially for every multi-agent teams, we have collaboration where multiple units or agents are working together. And then we have stuff like communication and coordination. So task allocation and scheduling that we talked about is specifically limited to coordination. Now, your question would be in collaboration and communication, and there are works that have been conducted. So communication is one of those human-robot team challenges that's still going on, and you can actually use graph neural networks to represent that network of communications, and it has been conducted by previous students from our lab, like Ismail Seraj and Rohan Palija. And as far as collaboration, where you have a robot and a human working together, that would involve some form of communication as well. But it would also lead questions like who's in charge? Who's the one making the final decision? Is the robot in charge, or can the human overrule their decisions? So in the context of table tennis, let's say, there is a recent publication by Kinman et al., who have gone into user experiments on how humans react to robots taking charge, saying something like, it's my turn, over letting the human dictate that relationship.
It's complicated. What do you think should happen?
I think at the end of the day, humans should have a final say, especially if it involves themselves.
How do you develop trust between a human and a robot? Because, okay, I'm saying this from my perspective. If I was put in a human-robot team, it would take me a while to get accustomed to my robot friend. How do I build a better relationship as we work together?
That's a still developing field, I think, but there are questions you can ask, such as, how competent do you think the robot is at a given task? So it's to rephrase what I previously stated about perception. There is the robot's actual competence of completing a task safely, and then there's the perception of competence, where a human observing the robot decides whether or not the robot is competent. So this is an entirely personal question. It varies between users. So I would say it is a field that is developing and more research needs to be conducted.
Let's focus on the scheduling algorithm then. How do we develop trust with the scheduling algorithm and know for sure that it's making decisions that are the best for the team as a whole?
Yeah, so one of the fastest or easiest methods would be actually comparing the schedule to an optimal schedule from an optimizer, which might not be feasible at larger scales like we talked about. So then you have to look into actual metrics, which is what we did. So we have multiple constraints, such as order constraints, where a task has to be completed before another one. And you have to wait a certain amount of time, like saying, I just painted this wall and it needs to wait for a few hours to dry before further work can be developed. So those constraints will lead to the schedules either breaking or failing. So certain tasks may not be completed. So you can measure those and see how competent the generated schedule is. But then you can look into stuff like workload, where you have multiple agents and how much work are they given? How often do they work? Is one agent given every task? Or is one agent given only tasks during a certain time period? And these are definitely metrics that need to be analyzed.
Taking this a step further, could we analyze workload, say burnout from an agent? Is it possible to incorporate wearable technology and provide that information into the graph neural network to make better predictions about what the schedule should be?
I think that's possible. I think it's an interesting future work to consider for HybridNet, but not just HybridNet, but all other scheduling work.
Graph neural networks, they can do amazing things, but there's a black box nature associated with it as well. Sometimes me as a human would want to know, okay, why was I assigned this task, but the robot was assigned a task that I like to do? How do you make the systems more transparent and help the humans understand, okay, this is how the logic works behind the algorithm? Is that possible to do?
I think it's certainly possible. I think graph neural networks, like most neural networks, are treated as black boxes. And I think we should open those black boxes, make it accessible for humans to understand what's going on underneath the hood, so to speak. And explainable AI is has picked up on this problem, and it's trying to come up with solutions. There are definitely work that's being done on trying to generate models that humans can understand, and there are research being conducted on that field as well.
I see. Tell me about the importance of communication. We spoke about that as one of the grand challenges in human robot teaming. My mind automatically goes to a search and rescue mission where maybe you don't have the network bandwidth to initiate communication between different agents. How can we solve that issue? Because the real world is complicated. There are so many other factors you'd have to consider.
Yeah, for search and rescue, where you have real world, let's say drones doing the searching, and then you have ground vehicles or humans doing the actual like rescue by arriving there and executing a task, like actually doing the rescue. There are challenges involved, especially if you're looking to deploy in a large area where distance becomes a factor on communication. Like you said, bandwidth becomes a factor. So one of the options is representing that communication network between agents as a graph, and then you can control how much communication there's going to be. If it's full communication where every agent is talking with one another, versus if it's local where agents have a range where they can communicate. And with graph neural networks, it means that it can also account for stuff like that communication cutting off.
I see. There's definitely a balance you need to strike. Can you tell me about the trade-offs between the centralized and the decentralized model? It seems like decentralized would be faster, but what are the trade-offs you'd have to consider in a search and rescue mission?
So with decentralized models, you will not have a full understanding of the environment. You will only have a partial observation, and that will lead to decisions that may be suboptimal, that might look optimal for the case of that specific agent based on what it knows. So that's definitely a trade-off. Centralized models with full observation, being aware of everything that's going on, will have more advantages over decentralized models. But on the other hand, decentralized models are more adaptable to real-world applications. And I think both sides should be developed further to find a solution to this very hard problem.
What is the challenge within human-robot teaming that you would most like to solve through your research?
My focus has been on specifically improving the scalability problem and making decisions that are fast, not necessarily optimal, because with learning-based models, you are trading off training time before you actually deploy the model for faster decisions that are closer to optimal than what you might get with heuristics. But that will still be most likely suboptimal.
See, more practical because it's faster.
Yes, but the difference between pure graph neural network models versus HybridNet that we have worked on is that speed involved. So with sequential decision making, where a graph neural network would make a decision, update the environment, then run the graph neural network again to make the next decision, it will become a challenge to make all of those sequential decisions, and it will scale up with the number of tasks. Versus observing the environment once, rolling out an entire schedule, and then seeing how that performs. So how we do it is we generate a representation, an encoding of the environment through the graph neural network once, and then we take that representation and run it through an LSTM, which is smaller. It also does not require our model to update the environment, get a new observation, and build a new graph. So we have a smaller network generating a distribution based on an initial observation. And then we can essentially sample from it and roll out multiple schedules and see how they perform at a rate that's faster than just doing that cycle of building a graph, getting an allocation, updating the environment, building a new graph.
I see. How much time did this take you?
It took me and Jayon 2 terms, about 7 months to get started from idea phase to submission to IRAS for the paper. And this has not started from scratch. The ideas have been built up on previous works, like Sir Isaac Newton has said, if we can see that far, it's because we stand on the shoulders of giants. And there has been previous work on task allocation and scheduling from my advisor, Dr. Matthew Gombolay, and previous work on graph neural networks from various authors that have developed it for various tasks in not necessarily scheduling, but in recommendation systems and in scalable multi-agent robotics. And now we have works like Dreamer that have similar applications of recurrent neural networks to roll out the environment observation to generate a fast decision-making algorithm. And then, of course, Jayon Wang's previous work on actually implementing task allocation problems and solving them using graph neural networks with behavior cloning, so it would learn from an actual optimal solver, has been that they have laid the groundwork for our work.
I want to end this conversation on the note of lifelong learning. That was one of the challenges listed in human-robot teaming, and it's definitely one of North Stars that we want to strive for in terms of humans and robots evolving together and learning together. What is needed for us to get there?
Yeah, so first, if you're looking at teaching a robot, you need to look at how humans themselves learn. And like you said, lifelong learning is something that humans themselves do. We are not static. humans learn through interacting with other humans, interacting with their environment, and that learning process is continuous. So what we want is robots that are similarly able to learn, not necessarily once, but through observation, through interaction. And reinforcement learning has allowed us to essentially train robots through that interaction with the environment. But specifically online learning, where you can learn from your decisions over time and further optimize yourself, is also something that is needed to be done. So with the way that we have built HybridNet, it is technically capable of online learning. It can continuously interact with the environment and just improve itself over time. But then there are challenges associated with lifelong learning where you might get stuck on a local optima. So it's not a perfect policy, but just something that the agent is stuck on. And how can you differentiate between that and the actual optimal policy?
It's been a pleasure speaking with you. And for those of the listeners, Batuhan, I just want to say that beyond his research, more than anything, he's an extremely kind individual, and he's a great mentor to people who want to enter this field. And that's kind of what his lab does as well. So I wanted to thank you. Very grateful for your time, and I enjoyed this conversation.
Yeah, thank you for having me.